This is the second, the last video on the, the topic countability of sets. And in this lecture, we will discuss some standard exercise on countability. So the first one, which says that if we have any infinite subset of a natural number, then it has to be a countably infinite. And in fact, we have used this uh, idea in one of the proof which I have left incomplete. So you can use it, you can prove it using the same idea. Okay, so basically this all is true, because this is true because we know that if we have any subset of a natural number, then we can list them in a increasing, and the elements can be listed in an increasing order. So the element can be listed. So listing basically means enumerating. So once we know how to enumerate these elements, infinite elements in that particular set, it might be finite or infinite. If we know how to enumerate, once it is done, we can so that means we can correspond each elements to each natural number sequentially. And so we have one to one correspondence between that particular set and the set of a natural number here, because we want to show that an infinite set is countably infinite, so it is countable. Okay, so if it is a finite set, if it is a finite set, then definitely it's a finite. If it's an infinite set, then it has to be countably infinite, to be more precise, not just countable, it is countably infinite. Discuss the proof of this statement. First of all, note that A cannot be empty. I mean, that subset of n cannot be empty. So, if we have A of natural number which is infinite, then he is not empty, as he is not finite. If it was, I mean, uh, if it is empty, then that would imply that A is finite. Okay, so since it is infinite, I can, and it's a subset of a natural number, I can apply a well altering property. Therefore, by well altering property, A has a least element. Okay, so let me call that least element as R1. So let R1 be the minimum of this set A. Okay, so we remove first the minimum among all the elements of A. Then I'll consider the set A difference R1. Then again, if I consider A difference R1, this also have to be non-empty. Okay, because, and also this is infinite, because if this is empty, then this would imply that A contain only one element, which is finite. So that is the contradiction. So infinite, when the set is infinite, you may remove as many elements as you want, the set will still remain infinite. Okay, and so to show that it is finite, so if infinite, if it was finite, then again you will see that A, which is made up of A difference R1 union R1, being a union of finite set, is finite, that's again a contradiction. So therefore I've justified both this statement that A difference R1 singleton R1 is non-empty, and it is infinite set. So in fact this idea can be used again and again, as we will be having infinitely many such Ri. Okay, so again you note that is contained in N. Okay, and therefore it has a list element. Okay, such that A difference R1 is non-empty. Therefore, there exists R2, a list element of A difference R1, and the relation between R1 and R2. R1 was the least among all A, and R2 is one element from A, so obviously R1 have to be strictly less than R2. R1 cannot be equal to R2. Okay, so R2 belongs to N, says that R2 is the minimum of A difference R1. Okay, so therefore R1 has to be less than R2. So since it's a infinite set, we have to keep on doing this process inductively. So for each n in N, we have Rn, which will be minimum of A difference R1 R2 till Rn minus 1. Okay, sorry, till uh, yeah, Rn minus 1. So next, to get this R3, I'll remove R1 as well as R2 from the set A, and R3 is the minimum of A difference R1 R2 R1 R2, and we go on. So inductively, for each n in N, we define Rn to be minimum of, as per the definition, just look at this, it is R1 R2 till Rn minus 1, right? As R2 is minimum of A difference R1, R1 is the minimum of A itself. Okay, and note that again this A difference R1 R2 till Rn minus 1 is non-empty, and it is in fact again infinite. Okay, for each n in N, and therefore we have A see A, this each Ri is coming from A itself. Okay, so since it keeps on moving like this, we can, even after removing so many elements, still A remain empty set. So I can claim that A is nothing but it is made up of such Ri, where I is varying over the natural number n. Okay, which is a subset of n. Okay, with the property that Ri is strictly less than Ri plus 1 for each I in N. So now this gives us the idea. So we could enumerate the element of A in such way: R1 is less than R2 less than R3, and this goes on, less than Rk less than Rk plus 1, and this process goes on because it's a countably infinite set. Because it's an infinite set, not countably infinite. So we are proving that it is countably. So what is that bijection that you can produce from A to the set of natural numbers? So that is natural over here. Define A to N by f of Ri is equal to I. So definitely this is an 1-1 map, because I will be equal to j provided Ri is same as Rj. All these elements are distinct, and so since each elements are distinct, they will be mapped to a distinct element in N, and it's on to map for any natural number. We can find an element in A. say for j in n, I can find rj which will be in A such that f of rj is equal to j. So f is bijection, and once it is bijection, A is countably infinite. So that's the result of the first exercise. Second, here open interval 0 comma 1 is uncountable, and in fact in general a comma b where uh, a is strictly less than b is uncountable, and even for that reason you may consider the endpoints, still it will remain uncountable. So we will prove that for 0 comma 1, and it can be extended to it can the result can be generalized for any open interval, as we know that there is a bijection between 0 comma 1 to any open interval of the form a comma b, as well as there is a bijection from open interval to closed interval a comma b. Okay, so we first write down the result proof for this. So the proof is by contradiction. If we say that this is countable, which means that every element from 0 comma 1 can be listed down, can be enumerated. Okay, so suppose you have a bijection n to 0 comma 1, n to 0 comma 1 I'm taking, so that it will be better for us to write down the element, the listed element. Okay, so now what will happen, that each f of I will be 0 comma 1, and you can see that this means that each f of I can be written in this form: 0 comma ai1, ai2, ai3, and this goes on. This is in fact this keeps on going, a non-terminating decimal expansion, and you can see that if this at certain points after certain stage, if it is if all this such ai's are equal to 0, aij's are equal to 0, then again it becomes a exact number. So here what we want is that what we know that each f of I, since it belongs to 0 comma 1, it can be written in this form, and so we list down all such f of i's, all such uh, number. So the first number will be f of 1, which will be 0 comma a11, a12, a13, and this goes on. F of 2 will be 0 comma a21, a22, a23, and this goes on, and this goes on till say f of n will be 0 comma an1, an2, and this goes on till say an plus 1, and this goes on, right? And this keeps on moving. Okay, so in this way, if f from n to 0 comma 1 is a bijection, by the statement it says that, by our assumption it says that we have covered all such decimal expansion which lies in between 0 comma 1. So which that means for each I in n, we since this map is on to from n to 0 comma 1, for any element in lying in 0 comma 1 there is a natural number I, such that f of I is equal to that element. Okay, but with this arrangement we can still say, we can still produce an element which lies in 0 comma 1, but it do not have a pre-image. So for that reason I'll define an element in this way. I'll define bn to be ann plus 1 if ann is less than 9. Okay, and I'll fix it as 8 if ann is equal to 9. Number 1 less than 9. Okay, so now you can see that this ANN plus 1 will not occur anywhere in here. So just look at this. uh, this Bn cannot be f of 1 because it do not have a11 plus 1. It has a11 plus at the first place. Then it cannot be f of 2 because it do not have a22 plus 1. Okay, and this goes on. Okay, and because of this, if I consider, in fact I have not given you the number which I'm considering b to be 0 comma b1 comma b2 comma b3, and this goes on. So now if you look at this, this number is nowhere appearing in this f of 1, f of 2 till f of n. The reason is very simple, because if I consider, see, the first decimal place is ANN plus 1, A11 plus 1. So here f of 1 is A11, it's not A1. It cannot be f of 2, it cannot be f of 3, nor it can be any. It cannot also be f of 1 because the first place over here is A11 and not A11 plus. Second thing, it cannot be f of 2 also. Just look at this B2. B2 is what? AN and B A22 plus 1. So here you don't have A11. Here also you don't have A22. You don't have a22 plus 1 as required, and so therefore it cannot be f of 2, and like this it cannot be any of this f of I, and therefore we don't have any pre-image for this b. Definitely this b lies in 0 comma 1, right? Okay, and b is different from each f of n as n belongs to n. Okay, hence f is not onto, that's a contradiction, and therefore our assumption that 0 comma 1 is countable is not true, and therefore it is uncountable. So our next standard exercise is actually dependent on this. We say that the set R is uncountable. Okay, so the proof is also with the help of contradiction. If I say that R is countable, then we can produce, that there's a map from 0 comma 1 to R which is onto, or in fact which is injective. Okay, and that map is defined by f of x is equal to tan of x pi minus pi by 2. This map is injective, so you can check that f is injective. Okay, so now since f is injective and R is countable, this imply by one of the property of countability that 0 comma 1 is also countable, but here we know that this is uncountable. Now why we are getting this contradiction? Because we have assumed that R is countable. So q plus q minus and q, the set of rational number, unexpectedly is a countable set. Okay, as well as n cross n is countable. So first we will prove that n cross n is countable. It's enough to produce a 1-1 map from n cross n to n. And what is that 1-1 map? We have already learned about this, defined by f of m comma n is equal to 2 raised to m into 2 raised to n. Okay, sorry, 3 raised to n. So this is an injective. In fact, it is, if I'm not wrong, it is bijective map. Okay, and therefore n cross n is countable. Using the fact that n cross n is countable, now I can show that q plus is countable. Okay, that is what you can do is that you can produce a mapping from n cross n to q plus, which is surjective. Okay, so I'll produce a mapping from n cross n to q plus. Why we want it as a surjective? Because q plus coming over here as a codomain. Okay, if you wanted to produce, you can also produce a injective map from q plus to n cross n, but it is very easy to produce a surjective map from n cross n to q plus, and it is defined by g of m comma n as m by n, a very simple map. Okay, since it's a natural number, this will be a positive rational number. Okay, and this is surjective. Remember that this is not an injective map, because you can very easily find two pair in n cross n which map to the same element. So this is surjective, and therefore q plus is countable as n cross n is countable. Okay, and using the similar idea, you can show that q minus is also countable. What is that map that you can produce from n cross n to q minus is, okay, in fact I'll define g minus just to make it different from the above notation. So this is also a surjective, and therefore it is countable. Okay, to show that q is countable, in fact, to show that q is countable, we make use of the fact that z cross z is countable. Okay, I think that would make sense, right? So z cross z, I'll take h defined from z cross z to z cross z to z star means it is a set of integer except 0 to q, defined by, okay, h of m comma n is m by n. N is non-zero because it is coming from the second Cartesian product. Okay, second set of the Cartesian product. So this also you can prove it as a surjective. Now here z and z star are both countable, so therefore the Cartesian product is countable. So since it is countable, here q is also countable. Okay, so using the same result which you have used above. But the set of irrational number is uncountable. The reason is very simple. If q complement is countable, then what would happen? Note that R is the union of R different q union q, right? That is set of irrational plus rational. Now here I am saying that the rational is irrational is countable. Rational, you know that it is countable. So therefore this is union of countable set which is countable. Okay, it's countable as union of countable set. But this is the standard set R. We know that that's a contradiction. It cannot be a countable. It is uncountable set. So that's why our assumption that irrational is countable is not true, and therefore it is uh, uncountable. One last one, p of n, the power set of a natural number. Again, if this is countable, then what will happen is that if it is countable, then there exists an onto function from n to pn by the property, but that this contradicts to Cantor's theorem, right? If you remember Cantor's theorem, it says that there is no onto map from n to p of from x to p of x, where x is any subset of a natural number. Okay, so with this I'm done with the topic countability. Okay, Uh, if you are very keen to see some more exercise on the countability, you can refer the textbook by Foundation of Mathematics by Kumaresan, okay, Baba Kumar Sharma and Ajit Kumar. In the next video, I'll be discussing the equivalence. I'll be discussing that the three principles of inductions are equivalent. Okay. Thank you for watching this video.